All right, so I believe that now this is recording, just in case you lose the connection. And you guys hear me well. So let's start class. So we were talking about scattering by crystals, right? So just as a form of review, we have talked about how atoms in a crystal are really organized. Their overall structure can be reduced to a small group of atoms, that's the basis set, and that small number of atoms, that small group, is repeatedly put in a position that we call the space lattice. So that's how we get to a crystal, right? So we have that the space lattice is given to you by translation vectors. So we had these translation vectors, we have some integers, and then some A1, A2, and A3 vectors. And H, K, and L were numbers, integers. So this space lattice has translational symmetry. And then there's other symmetries depending on what space lattice we're talking about. And these symmetries are due to the repeating nature of the lattice. We also have a basis set. So this imaginary, I don't know if I want to call it imaginary, but it's like a mathematical object, the space lattice. I want to make sure that this is clear. This is a mathematical construction. It doesn't tell you anything yet about the atoms inside. What you do after that is that you have atoms attached to this unit cell defined by that space lattice. So then we have these basis vectors. And this, guys, is where you would put the atoms. So we have a set given by Ri. So remember, this is a set of vectors. And this xi, yi, and ci, those are fractions. It doesn't have to be 0, 1 like integers. They can be whatever number you want to have. So with this two, the t vector, that's the space lattice, and the set of vectors in your basis set, you can define the location of all of the atoms and of each of the atoms in your crystal. So any questions up to here? This is just kind of review, right? Just to refresh you on the definitions.
Just a little question, which is, if if we want to define the position of each and every atom, the basis vector is enough for that, right? But we also have this base lattice, which is if we want to specify any position which is maybe between the atoms, for that we will need this base lattice, the translation vector as well, the d.
So
But
the
just
t vector, so
mhm,
let's say we had a unit cell, right? Let me try to draw it. So let's say this was your thing that goes to infinity, right?
mhm,
So your R vectors are going to describe, let's say, two atoms, one here and one here.
right.
And then this little square is repeated here and here, here and here, here and here, like that. So there's a unit cell. You can call one a special one that we call, let's say, the origin. It doesn't have to be special, but let's say this was the origin one.
Mhm,
Then this basis said this T would be this point, let's say, and this is your R1, and this
Oh, I see.
atom would see your R2.
Hmm.
But then let's say you want to talk about another atom in that same crystal. You want to talk about this one, then you have to go 1, 1 in the T from this guy, right? No, wait, from this guy.
Yes.
Or if you wanted to talk about this one, then you have to go and translate by this vector, which is one of the vectors that we have in there, in T.
So R is giving you the position of the atom in a single unit cell, and T is taking you to any other units you want to go to.
Yeah, so T can take you from this guy to that one, from this guy to this one, and so forth.
Okay, okay. Yeah, so and in this case, I would be 2 because we have 2 atoms in a unit cell. So I would have values 1 and 2. Okay, excellent. Yeah, that's very clear. Thank you.
All right. So the next thing I wanted to talk about is that you have, again, this is kind of like a review, but this is something new too, okay? Because I just told you, assume that this exists. I didn't explain it. So this is, the next part is all the new stuff. We have incident waves. And then let's say that we had an atom. So here's our atom. This is the nucleus. Then that nucleus has some electron cloud around it, right? And then we have that there's incoming radiation. So these are plane waves coming at it. They're moving in this direction. There's an incoming vector for this wave. And then this atom is gonna reflect or scatter that radiation in this direction. Wait, is KS. So this is the scatter radiation. So what happened is that you could have any waves that you want and scatter them off of this atom, right? But the wavelength of X-rays is at the right scale for the lattice spacing of crystals. Neutrons, electrons at the right energy, neutrons at the right energy would also have the same, kind of like the same wavelength, so that you can probe the distance between atoms in your crystals. But X-rays are way easier to make. And that's why X-rays are used a lot. For instance, you could go to a neutron source in Oak Ridge to do the same experiments that we're talking about with X-rays, but instead of X-rays, you would be using neutrons. And the other thing that I told you before is that we were going to ignore that the atoms are vibrating. So we assume that they're all fixed in space. But this is kind of new. What I didn't talk about is that there's a little vector right here from this position on the center of the atomic nuclei to here. There's a little volume right there. So let me call this vector R. And this right here is a three-dimensional volume given by this. All right, any questions about the geometry? All right, so we have a structure factor. And before I told you it's just a number, right? The reality is that the structure atom is how this incoming wave is interacting with the electron density of the system. And what you do is that you would integrate over the volume that is affected by the atom. The electron cloud is around the atom, right? And then you will have to integrate the density, the electron density, that cloud, over position space, and then multiply it by this Q dot R exponential. And again, the integral is overall space that is affected by the atom, wherever the density is not zero. So this is what you do. That's the structure factor. All of the electrons in each of the atoms that you're heating with X-rays are going to have an electron density. That electron density is given by this quantity. And the electron distribution is what gives rise to the atomic form factor. So for instance, this guy could be an atom that has 4 orbitals in that particular direction, right? If it's hydrogen, it would have just the 1s orbital. If it's carbon, it has the 2p, 2s, and so forth. And the atomic form factor is, let me plot it right here. So here I would be plotting this F of Q, the atomic form factor. And then on the bottom, I would have something that is Q, is the sine of theta over the wavelength, and this would be the definition of Q, and it's in units of inverse angstroms. So let's say 0.2, 0.4, 0.6, and it keeps going in this direction like that. And for each particular element, you could plot it. And in this case, it could be, it looks like this for carbon. It looks like this for sodium. It looks like that for oxygen. Chlorine. And then iron would be over here. And it's just decreasing like that. So the two features that are important here is that the atomic form, this is the atomic form factor as a function of the scattering vector Q. And the most important thing is that f of Q is proportional to the number of atomic charge of the system, right? So for instance, iron is way higher than carbon. Why? Because iron has way more electrons. And the other thing is that when Q goes to 0, then f of Q is approaching this value of C. So you see it here, carbon and oxygen are close to each other carbon and oxygen are close to each other away from Q is equal to 0, but there's a difference in the number of protons inside carbon and oxygen. So therefore it's not the same value when Q goes to 0. But the reality is that it's just a multiplicative factor that you have to account for in each of them. And these are calculated. They're also obtained experimentally. So you can look them up in tables when you're looking at forming the whole XRD spectrum that you need to form. All right, any questions so far?
So sodium and oxygen are really close at Q equal to 0 because it's 8 and 9, very close Z numbers. Is that happening? Okay.
Yeah. And chlorine is way higher, right?
Because yeah, it's like 19, 17,
yeah.
19, something like that. 17,
right.
19.
So need a new page. So the thing that we're thinking about is that what I have just told you is the atomic form factor And you could calculate the X-ray scattering from, let's say, whatever many atoms you have in your crystal, right? So you can treat each atom as a scattering particle, and then each of them has an atomic structure factor, and then you can calculate what is the intensity, which is calculated from that structure factor, multiplying from different atoms coming together, and you get interference from all of the atoms in the crystals. But that's really hard because you might have 10 to the 23 atoms in your crystal. So what you want to do though is that we have an ordered crystal. So we can take this shortcut where each unit cell is identical to the other, and we treat each unit cell as a particle. So each portion in the unit cell is a particle. And then you can calculate things. So in this sense, what you're doing is that your structure factor for the unit cell is given by a summation over whatever is in your bases from each of your little cubes, right, that you have. Here is the atomic form factor from each of them. And then you will have this multiplicative with the positions in there. So what do we gain by doing this? The first thing is that if you were doing, when you're doing experiments, you don't just do one experiment. You do a bunch of experiments and then I try to iron out all of the noisy details by doing ensemble averaging, right? In this case, by doing it over a single unit cell, because all of the unit cells are identical in our crystal, then what we have is that we have a symbol average already what we have. So a symbol average is already taken care of. And then the other thing is that once you have the intensity from one unit cell, with translation vectors, we have the intensity for any of the arbitrary unit cells along the system. Does that make sense? So just doing it for the unit cell, then you just have that all of the unit cells are identical except for this additional portion that we need to do. All right, so now what I'm gonna do is that I'm gonna have the structure factor for a crystal, okay? And basically, this is the structure factor for the crystal would have this is the symbol for a structure factor, the S. And this is over n unit cells. So that's the n that I have right there. And that structure factor will be the summation on the I direction, summation in the J direction. It depends on this Q vector, which is given here, the dependence. And then we just have to go through the positions in unit cell I and unit cell J. Questions there? All right, so I can talk about unit cell I or J as separate things, or I could rewrite them and just graph. So I have the same thing here, same thing here. And then this is gonna be dotted into, and now I have the position, original position, plus translation that would take me to that particular atom in unit cell I, minus our original position, plus the translation vector that takes me to that atom in unit cell J. Questions?
So we're dividing it by n to normalize the...
So this is the structure factor for the whole crystal, and we're going over n unit cells.
Yeah, but I mean, we're dividing by n because, I mean, why exactly are we dividing by n?
Because we have n unit cells in our crystal.
I mean, does that like sort of normalize the
Yeah,
final?
kind of like normalizing it.
Oh, okay.
So then these two guys up here, I could rewrite it as, I mean, once you look at the form here, right? I see that it's just a simplification. And I have just one unit cell squared. All right, so this is something that kind of like exactly I had worked out how to do it on the previous one, but this is how it would work for a crystal. We were looking at a single row of atoms, right? Now we have a crystal here. From here, we see that there's a particular Q that is going to give you the biggest intensity, right? So we have to look at this portion right here. What Q gives you the highest intensity? So let me ask somebody. Garrett? What Q gives you the most intensity? Garrett, you there?
He answered in chat, I think.
Oh, okay. So you say parallel to TI. So can you be a little bit more specific than that? Yeah. You can type it in. So you're saying parallel, but it's not just the parallel one, right? We actually want to maximize this monster. All right, so what we want then is a set of vectors, oops, a set of vectors that, let's call them G. When you dot them with TI, give you either 0, 2 pi, 4 pi, and so on, right? And if you have that, e to the 0, e to the 2 pi, e to the 4 pi, they just start adding up as ones. Those are actually the only ones that work, because if you had any other values for the Q, then you're gonna get zeros. Like let's say you had the pi, you had 0, pi, 2 pi, 3 pi, 4 pi, then you're not getting 1, 1, 1, 1, 1, right? For those particular Qs, you're getting 1, negative 1, 1, negative 1, 1, negative 1, and you don't add them up together. So in fact, these are the only ones that give you constructive interference. And that's the key. In fact, this is three-dimensional. So what I need to do is rewrite I can rewrite this as of Q. And in this case, I will have 1 over n. And I'm going to have three indices. So we start with h is equal to 0, and 1 minus 1. And then I have e to the ih Q dotted with A1. And then that gets multiplied by exactly the same thing, except now is the K is equal to 0 and 2 minus 1. That's the summation that we're doing over e to the negative ik. That K is the integer Q dotted with A2. And then the third one that has the L is equal to 0, N3 minus 1, and then it would be e to the negative IL, Q dotted with A3. So what I've done is that I have taken apart the vector Ti to put it in there. That makes sense, right? And this N is N1 times N2 times N3. So we have this many lattice points in our crystal N, and it goes N1 in one direction, N2 in the other direction, and N3 in the other direction. And what we're doing then is that each of the summations, for instance, this one right here, is a summation along each of the crystal directions. Okay? Any questions?
Yeah, if I can ask.
Yeah, go ahead.
If you want to go first, no problem.
What is this S crystal actually means? What did we find here?
So that's the, so the intensity of the X-ray is gonna have two components. One is coming from what type of atom you have, right? Mm-hmm. And the other one is coming from the positions of those atoms. So in this case, I'm taking, this is intensity again, that's why it's the square, right? Of positions. So I'm taking the atom, the atomic monster or whatever the structure, the atomic structure factor away from this, and I'm just writing what the intensity would be as a separate entity that doesn't have yet the contribution that comes because this atom is this value and this, like this atom is chlorine, this atom is sodium. So I haven't put that back into the equation to get the actual intensity. So this is just the spatial nature of the crystal lattice gives you this thing that I'm calling the structure factor of the crystal. Just the positions of the atoms, not the actual nature of the atom.
So it's basically this will, with combinations of the additional info, it will give the basis of the crystal.
It will give you the intensity in your XRD, the intensity of the X-ray diffraction lines. This would tell you where the peaks are. The other guy, which is atom dependent, would tell you how big those lines are.
You said this gives you position, right? Not the amplitude.
Right, the position. Yeah.
Thank you.
Dr. Barunda, may I ask one question?
Yeah, go ahead.
You said that the structure factor just give the position in the XRD, right? So it means we are looking for the element identification, like we just compare the XRD peak with its generic peak, and we just compare which element is this. For this purpose, we need a structure factor.
Right. So that's what this guy is giving you. This structure factor, the crystal structure factor, is exactly doing that.
And what about atomic structure factor? By that, we can get the intensity amplitude as well, right? So we can we may know the maybe the different another properties of this crystal, like I mean its thickness, or like the difference between two position, like different points.
Yeah, exactly. And that would go, well, the thickness could be that you're going in this direction versus this direction and this direction more. So let's say N3 was along the axis, one of the symmetry axes was also the thickness of your film.
Yeah,
The
like
tree might be just a couple of layers, right?
yes. And like I mean, like if you want to calculate the full width half maximum or something like that, atomic factor would help us, right?
Yes, yes.
Okay, I get it. Thank you, Dr.
All right. So then, if you look at each of these sums in the summation, let me separate them. You can do this because we already did it in the previous class. We had a single line. Now, each of these guys is coming out like this. And then on the bottom, I have the same thing without the n, right? So this little curly bracket is the intensity from one line of atoms. And that's what we did in the previous class. And then I will have another bracket that goes with the N2 and A2 vector. Same terms, you just switch those things there. And then another bracket, that summation would be related to the N3 integer and the A3 direction. So those would be after you do the summations and interference. So we have, in each of the bracketed terms, we have the interference of waves by a single line of equally spaced particles, except that our particles are not really particles, they're unit cells, right? And this is, if you look at it, this is what Laue was doing, right? Laue was copying or grabbing something from optics that we know really well. Well, maybe not really, really well because we don't teach it as much. But if you look at the diffraction grating in classical optics, the light reflected has the same form as these bracketed terms. And these are identical to those mathematically. So this is what we have: interference of waves by a single lines of equally spaced particles, or unit cells in this case. So any other questions about this? The scattering?
Yeah, very quickly, is the sign squared? Because last time for the 1D, I wrote it down as sine square.
I believe it might be. Let me look at my notes from the previous time. Because yeah, the previous times yeah. So for intensity, sine is a square.
But in this case, it's not square.
In this case, it's not square because that was the square of the intensity, right?
Okay, okay, I see.
So this is just before taking the square. Yeah. So before I called this something like this. And then we had to square it to get the intensity. So what I have here is that this structure factor is the product of those three brackets, and that the intensity of the scattering is going to happen. So this is where this is interesting, right? So I want to get the intensity, I have to square it. But then each of those brackets is only going to contribute, it's only going to be contributing when that thing is maximized. That Q has to maximize, whatever Q we choose has to be maximized in all three of the brackets. So that makes it so that you have the Laue conditions. So each of the point in your lattice is going to contribute if it's maximizing all of the three brackets. So we have that Q times A1 has to be 2 pi h Q times A2 has to be 2 pi k, and then q times A3 has to be 2 pi L. Q, remember, is this vector minus this vector. If Q does not satisfy all three equations, then you don't get any scattering. So that makes it there's very important directions that are gonna allow scattering. There's very few of them, and all the other ones don't allow scattering because one of them might be 1, but then the other one is gonna be 0, and you're multiplying ones by zeros and you get 0. So then at this point, let's go back to this guy, the reciprocal lattice. And
Can I ask a quick question before?
Yeah, go ahead.
So I'm trying to make sense of this. So I see that Q would have to be optimized with A1, A2, A3 if we were shooting the X-rays in any direction. But let's say we align the X-ray plane with one of the lattice directions. Wouldn't at least one of the two, either A2 or A3, become irrelevant?
So for
scattering.
What you want to do is make sure that that Q works in 3 directions, but now you can have planes where one of them is not important. So I'll get to that right now.
Oh, okay, thank you.
But the reality is that you have a special, so you have this H, K, and L are related to your unit cell, right? What position is this unit cell in the whole crystal? And that means that you have a particular lattice point. So there's a discrete set when Q is equal to GI. So you have the GI. In this case, this G vector, we could index it with I, but it's better to index it with these 3 parameters, HKL, and these are B1 times H, K times B2, and L times B3. So for each of those H, K, and L's that you had in real space, now you have an H, K, and L vectors. Oh, and just so that you guys remember, H, K, and L are all in the integers, right? There's one that satisfies the conditions. So that means that BI dotted with AJ is gonna be the Kronecker delta. And this Kronecker delta means that if I and J are the same, you get 2 pi. If I and J are not the same, you get 0. So if you have a real space lattice, right, the one's given by the T vector, you also have a reciprocal lattice, the one's now given by the G vector. This is my reciprocal lattice. Whatever lattice you have in real space, there's an equivalent one in reciprocal space. And this G gives us a roadmap for what is the diffraction coming out of the crystal. You can think about it, if you're familiar with this, as the spatial Fourier transform of the space lattice. So it's a one-to-one relationship that you have between the T and the G. And it tells us where scattering can happen. When is the Laue condition met for that particular set of lattice points in your crystal? Yeah, go ahead.
Dr. Bruno, how is it physically possible to have reciprocal lattice?
So that tells you the direction where things are gonna be scattering off. So I can do an example, which is something that I didn't have time to do last time. So let me do this example real quick, okay? So let's say that I had so I don't know why sometimes this moves. Yeah, I guess I can control it with my fingers and move it around. Simple cubic lattice, okay? This is an example. So in the simple cubic, you have 3 vectors. The simple cubic is the simplest one. And these vectors are your unit vector in the x direction, your unit vector in the y direction, and they're all the same size a, and the unit vector in the c direction. So this is the space lattice. So if I look at it, my requirement is that b dotted with a vector b dotted with a has to give me 2 pi if they're the same. So that means that b1 is 2 pi over a in the x direction. b2 is also 2 pi over a, but in this case in the y direction. And b3 is 2 pi over a in the c direction. So if you have a cubic cell or a square cell, this distance is a. This is a1 in that direction. This is a2 in that direction, and presume that a3 is coming at you perpendicular to the paper. That's the real space lattice. And this is the reciprocal lattice. You also have the same thing, except now this distance right here is 2 pi over a. And then you have that b1 and b2 are also here. b1 is pointing in the same direction as a1, b2 in the same direction as a2, and b3 pointing exactly as towards you as a3 was doing. So that's for the simple cubic. So you have that the same space. It didn't change anything. If you had a simple cubic in the space lattice, real space lattice, you have a simple cubic in the reciprocal lattice space. It's the same lattice. Now it just tells you those points are the same, but they're separated by 2 pi over a instead of being separated by a.
So the domain was just redefined, that's it?
Yeah.
But physically, nothing changes, right? We don't observe something
your
nearby.
representation is about wave vectors. It's not exactly the same thing. This is like a representation in momentum space versus a representation in real space. But what the lattice is telling you is what are the important symmetries of the system. There's still the same symmetries that you have here are the same as the symmetries you have here. That didn't change. That's why they look identical.
So, if I just may intervene, I mean, if you're thinking of like a real physical reciprocal lattice, it's not a real thing. That's the thing you have to, like first realize. The reciprocal lattice, it's not real. It's made up, obviously. Like phase space it's not real.
They're real. It's just that you just don't perceive it, right?
I mean, you can't touch it in that sense. Not like real space. It's not real, like physical.
Yeah, but I wouldn't say that it's a mathematical construct. It's like the dual space. So we have to think of ourselves as beings that live in a 6-dimensional space.
Yeah, I mean,
you only see 3. The other 3 you infer.
Yeah, so it's like it's not strictly real. So if you're thinking of a real, like a real space lattice is a real thing. Whereas the K space is not real in that sense. It's a translation from it's a conversion. It's like phase space, like we did in classical mechanics. The phase space. It's not out there real. The phase space, right? It's like that. So I mean.
Yes, Dr. Brunda. Also, you did this G dot A, right? So this flower equation has this delta K definition instead of GA. I was wondering what is the what is the reformation you did here. So normally it should be outgoing wave minus incoming wave, and that should give this wave vector. But in your case, it's we called it G dot A, right? Sorry, Q dot A. So it's the charge dot product with A.
Yeah, so when you have to have that Q, whatever vector Q is, dotted with A1 gives you 2 pi H, where H is an integer.
Yes, but I'm looking at the Wikipedia's definition. It says, instead of the GA, it says that wave vector is outgoing wave minus incoming wave. I was wondering, is it the same thing?
Oh,
Q dot A.
I just call it a scattered and incoming, but it's the same thing.
But you did dot product, that's the thing. Which, did you include both of them?
So my Q is a scattered minus incoming wave vector.
Oh, we just call it Q, but what it means is, oh, I see, good. It's Q2 minus Q1, outgoing minus incoming.
Exactly.
Okay, take care.
All right, so let me give you, I have these slides. I don't know if you see them yet. Let me know when you see them. You see them there?
Yep.
All right, so I need to minimize you guys. So if you chat, use the chat or something else, speak up so I can go look at the chat. So this is my lattice in the cubic cell, right? So you have very simple, let's see, laser pointer. All right. So this is your very simple unit cell, the cubic cell. There's a point at 0, 0, 0. There's one at 0, 1, 0. There's one at 1, 0, 0, so forth. So this guy has coordination number. That means how many atoms are near it. So you see that it has a coordination number of 6. And you can see it perfectly here. There's 6 atoms around it. 3 over here, 3 down here. If we look at the unit cell, it looks like this, the simple cubic. And for instance, in this case, this is the 0, 0, 0, 1. We also have one guy right here in the middle of that unit cell. So that's a cubic cell, and that would be the basis for it, right? 0, 0, 0, and 1/2, 1/2, 1/2 gives you the basis. So now when looking at the crystal planes, let's say we had a crystal, we have equally spaced parallel planes right here. There's
Dr.
one that is
Can I ask you one question?
Yeah, go ahead.
Yeah, but you said that A, B, A1, A2, and A3s are integers, but here we are using 1 over 2, 1 over 2. Am I confused somewhere?
So A is from here to here, from here to here, from here to here. That's A.
Oh, yeah.
And this guy are the fraction x1, x2, x1, y1, and c1 would be 1/2, 1/2, 1/2.
Oh, okay.
And then for this guy, the xi, yy, and cy would be 0, 0, 0.
Okay, okay. Thank you.
So then when we're thinking about crystal planes, you can identify the set of equally spaced parallel planes. Those are called the lattice planes of your system. So for instance, if this was your crystal, this is the plane that you go, this is the distance between this plane and this plane. You can have lattice points on each of the plane, or you could have lattice points that are on different planes. But there's an infinite number of lattice planes because you can define it almost anywhere. So then the thing that I wanted to talk about right now is the Miller index.
I'm so sorry, Dr. Brunda.
Yeah.
You showed them as being parallel with each other, but are they parallel in real life?
Mm-hmm.
I know that they're not parallel. I see. All of those planes, are they not randomly intersect each other?
No,
planes, lattice planes.
Yeah.
They randomly intersect each other, so it's not parallel, right? Like you've shown here, isn't it?
Well, actually, if you have a single crystal, they would be parallel to each other throughout the whole crystal. What happens is when you have two crystals, that are joined together, or a crystal that is composed of multiple grains, then you will have that there's an orientation in one half of the crystal and a different orientation on the other half. And those are really interesting. Grain boundaries, that's what they're called. But that boundary is, that would mean that you have two different crystals already. But in a single crystal, you will have, in a single grain, you will have that all of the crystal planes are the same and parallel to each other.
If they're not parallel, it's a different crystal, I see.
Yeah.
Okay. Thank you.
Mm-hmm. So now let's talk about these Miller indices, right? So there's a way to talk about the orientation of these crystal planes. And how do you make them? Okay, so let's go, instead of just telling you how to make them, let me go through the slide that tells you what an example is. So I took my simple lattice, cubic lattice, right? This would be the 0, 0, 0 point. This is the 1, 0, 0 point. So there's a plane that passes exactly through here. It intercepts x equal to 1, and then it goes in the c direction all the way to infinity. So it never intercepts with the c direction, that plane. And it never intersects the y axis. So that makes it so that this is the 1, 0, 0 plane, because he goes and intercepts the x-axis at 1, never intercepts the y-axis because he keeps going in this direction. So the intercept point with the y-axis is all the way in infinity. The same for the z-axis. And then you look at the smallest ratio. So if you take the reciprocal of this, 1 over 1 is 1. 1 over infinity is 0. 1 over infinity is 0. So you get the 1, 0, 0 axis. So this portion of the cube right here gives you the 1, 0, 0 Miller index. Now
You said 0, but you put infinity.
Right. So when does it intercept with the y-axis and with the z-axis? At infinity. So that means that the 1, 0, 0 crosses the plane 1, 0, 0 crosses the x-axis at 1. And then it never crosses the y and z-axis. So that
so it never crosses.
Miller index 1, 0, 0. Let's look at another one so that you can start visualizing them, okay? Here's another one. This one passes through this point, 1, 0, 0. And it also passes through this point, 0, 1, 0. And you can see that there's a plane that goes through there, right? So this is not just this little cube. It would be an actual plane that goes all over the space. So this one intercepts x at 1, intercepts y at 1, and it's going to continue to infinity and never intercept c until it reaches infinity. So therefore, the intercept point is infinity. So at this point, I take the reciprocals of that, and you get the reciprocal of 1 over infinity 0, 1 over 1 is 1, 1 over 1 is 1, and this is the 1, 1, 0 Miller index. Go ahead.
The problem with this I have, in concept, we can say it's infinity, but in an actual experiment, they don't intercept. So the z-axis doesn't exist. Why we call it infinity?
Well, it would not intercept it, right? Let's just say that it doesn't intercept it. So if you had a 30 layers, a thin film made out of 30 layers, and you put a plane in the crystal, it's gonna pass all across your crystal, and it's that plane, and it's not gonna be tilted so that it passes to C. That's, I guess, what I'm trying to get at. Let's see if the next one, you can see what the next one is and see if that solves the problem. There's another plane, and this one passes through 1, 0, 0, 0, 1, 0, and 0, 0, 1. So this one right here is giving you, this is the 1, 1, 1 axis, Miller index. And there's a point that it intercepts with the x, with the y, and the z axis. So now the thing about the Miller index, this is maybe where we're the visualization you need, Solfidin. The Miller indices gives you the planes that are going to be passing through your system all the way across. Does that make sense? It's not just that there's one plane. This tells you the smallest plane, that this, the smaller, the way to define it of the simplest plane, but there's a collection of planes that are all over the place.
Dr. Barunda, I have a question.
Go ahead.
You mean like a single crystal can have different Miller indices if you observe them from different planes, or these are all three different crystals?
So the same crystal, so the same crystal is gonna have planes that are separated by a distance d, and these planes are, the Miller indices tells you those planes that are available, and also it tells you in what direction are these planes that are all over the place in there, and also tells you basically how the scattering is going to happen on the crystal. So these are the three simplest ones. Let me go through the example now. Let's see. Let me go back to writing. Oh, I see something in the chat. Okay. Let's see. Did it start sharing or not really?
I don't see any image.
Not really.
Not really? Okay.
Gray screen. Oh.
How about there? Is it sharing?
Yep.
All right. So let's look at Miller indices, right? And how they work. So this Miller indices has a big role in the scattering because he has two things that he's doing. The first one is that he's telling you that this guy, this G vector, is normal to the plane. And then the other thing that he's telling you is that the magnitude of it is inversely related to the spacing of the plane. So there's not just one plane. When we're talking about the 1,0 plane, we're talking about all of the planes that are separated by the same distance, a unit of 1, that go just in the x direction. So I can rewrite these two things, and let's see, let me just put it here. This guy, the normal vector HKL, is equal to the normal to the plane HKL. And then what this one tells me is that the magnitude of this vector, so again, this little hat that looks like this, that means a unit vector. I don't know if that's the notation that you guys are used to. And the magnitude of it is related to the spacing between the two vectors, between two of those planes. So let's do an example. I like the cubic one, because that means that I can give you the phase center cubic one as your homework, right? So the cubic has these three vectors. Let's call it A3, A1, and A2. So this is a little bit hard to draw, but imagine this is the idea. This is your A3 going all the way across like that. And now what I have is this planes. Let's see, what color do I want to draw them with? I'm gonna have planes that go here. And this plane continues, right? It's not just gonna stop at that position when x is equal to 0. It continues in this direction like that. And up exactly like that. But actually behind it, there's another plane that is exactly there. Then there's another one. And I'm basically drawing when they intercept in that octant of that direction. That's what my plane is doing. So now if I were to grab it from the top, just looking at it from the top, let's say that this was a 1. Oops, that's crooked. And this is a 2. All right, so they're supposed to be the same size, so hold on. So this is a 1 and this is a 2. Assume they're the same size, right? Now, the plane that I'm drawing has 1, 2, 3 points in this direction and just 2 in this direction. And this plane, if you look at projecting exactly so that you're looking from the z-axis on the top, what happens then is that I have this point right here, this point right here, and this point right here. All right, so let me see if you have questions there. This part of the plane is this one. Is that clear? And I don't hear anything, so.
Yes, it's clear.
All right, Sulfidine, what is this plane that I'm talking about? Can you guess?
Oh, these are the Miller index planes you did in the previous slide.
Yeah, exactly. Which one would this be? Can you guess which one it is?
Oh, I don't see what you're pointing at.
This one. The first one. Well, they're all the same thing, right? The Miller plane, the Miller index is going to be the same for this whole family of
I thought the numbers should be different. This is like a
no, they're all the same.
101.
It's the set of all planes, right? But this
yes.
one, this one that I'm showing you is the one that lets you, well, actually, no, it doesn't let you see it all. You need to draw it all. But the idea is that all of them are identical in your crystal, and they're parallel to each other, and then you describe it with a single Miller index.
Yeah, so that's what I'm saying. I think it's 110 since it's A1 and A2.
Not exactly, because look, this is the distance from here to here, right? This happened at 1/2 and at 1 and at 3/2. And this happened at 1/3, 2/3, and 1. So when does it intercept the first whole number in the x direction, right? Is right here at 1/3.
It's the second plane, which goes to the integer number.
Then you take the inverse, and you get 3. Then the other one is at 1/2, 1/2, you take the inverse, and you get 2. And then it never passes through the z-axis, right? It doesn't intercept the z-axis because it's always parallel to the z-axis. So this guy is the 3-2 plane, 3-2-0 plane. So this one is not 1-1-0. This is the 3-2-0 plane. So I think that you need to grab it and play with it so that you start looking at how to make sense out of them. But this plane is not the same. So let me draw the other one. Let's say that
You said
the one, right?
Oh, Dr. Bunda, I'm so sorry.
Yeah.
You 3-2-0 is the first one close to the 0 axis, isn't it? 1/3 and 1/2. But then you pointed to the last one, which is 1 and...
Well, actually, they're all the same thing, right? The 3-2-0 tells us what these planes are. So the 3-2-0, there's a set of planes and they're all separated as the same distance from each other. They're parallel from each other. And this 3-2-0 tells you where they cross with that guy. So basically this one is actually 3-2-0. They're all 3-2-0. It's like a set of planes.
How would you do the second one? 2
Right.
2 divided by 3 and the 2 divided by 2, 1.
So for instance, if I had a plane that was crossing from the top, like this, right?
Yes.
What would that plane be? So this one is passing through, oh my gosh, there we go. There we go. Ah. Through 1/2 and through 1. You take the inverse of 1/2 and you get that gives you what?
Well, this gives 2, yes. But then what happens to 2/3? Inverse would be
1,
3/2.
So if you were to do the 3/2,
yes.
Yeah, so then you would just have to draw it. Like, let's say this is...
If it's a fraction, yeah.
Yeah. So this was 3/2. Then you would have this one here. And then it would pass through here. So you see, that's one of them. That one would give you the 2/3. So you can have different fractions of them and you can get what those planes are. All right, so what I wanted to show you then is that I can get, how do I get the magnitude of this G vector? So let's say this is my vector, right? The magnitude is by taking the square root of G cross with G. HKL, HKL. And if we do that, what we end up for the cubic one, we're going to get 2 pi over A and square root of H squared plus K squared plus L squared. Now, if I wanted to get the direction of the normal vector, in this case, let me also do the cubic one. What I need to do is get this vector divided by its magnitude, right? So if I have that, I have the vector on the top. The unit vector, sorry, I'm messing up. It's not, yeah, exactly like that. Divided by the square root. The 2 pi over a's are gonna cancel because they're on the top and on the bottom. And you get this. All right, so if we were looking at this plane, the 3, 2, 0 plane, So let me try to draw it out here. So if I'm looking at the G vector, the distance between planes in the 3, 2, 0, what I end up with is A over 3 squared plus 2 squared plus 0, the square root of that, and I get A over square root of 13. So that means that the distance from here to here is given by that A over square root of 13. That's the distance between those two planes. And then if I had to figure out what is the direction of this vector, I can get that the normal to the 3, 2, 0 is gonna be 3 in the x direction plus 2 in the y direction, because my h is 3, my k is 2, the L is 0, divided by the square root of 13. All right, sorry about the messiness on it, but that's the general idea, that now you have the distance between a spacing of those planes, and you can generate the directions that those planes are pointing in. So now you have that this direction, the one that goes like this is this normal vector, 3, 2, 0. And you know exactly the direction that it's going. All right, so I'm running out of time, so I don't get to do the XRD, what I wanted to do next is what is a plane, what is the scattering that is giving you, and how come some planes are gonna have a scattering from some particles and some planes are not. So we'll save that for the next class. You guys have any questions before we leave?
I have one question. So before, for example, when you drew these 3 planes in the 3 planes that are the same as the 3, 2, 0 plane. So beforehand, we didn't know the distance, of course, between the planes. So when we're drawing these same planes, but separated by a distance, what's the basis of choosing? For example, here we've chosen those planes which intersect in the A1 direction, do 1 by 3, 2 by 3. So how do I know that it should be a multiple of 1 by 3?
All right, so that's an excellent question, because that's what motivates the scattering question. So let's say that you had a unit cell that has an atom located here and an atom located here in that facet, and then it has atoms located here on that other facet. So that would be the plane that those three, there's a bunch of atoms, but there's this plane that passes from here to here.
So we should choose the spacing of the planes so that each plane acts kind of as a platform where you have these atoms.
Yeah, so if you have a system, simple cubic is very simple cubic, right? But let's say you had something more complicated, like a perovskite
Mhm.
or a zeolite or whichever real crystal that you guys can grow in the lab. Those guys are gonna have different planes. Like for instance, if you grow aluminum oxide, which I know some of you have grown, the aluminum oxide has a bunch of atoms in the unit cell, all of them at different positions, but you can look at those planes that are passing through the crystal and identify them and say, okay, I have a plane that goes from this crystal, from this atom in the crystal, and it's gonna touch all of this other, that's my plane. And you wanna see, is that gonna contribute to the XRD or not? And that's what I'm gonna cover. But basically, you're putting your atoms inside of that unit cell, and you're trying to figure out what are the planes that are important for scattering, and what angle should I put my detector in, or what angle would give me the right position for those scattering to happen.
Makes sense. Yeah, that would make things easier when you're trying to set up your X-ray in which direction.
Or
so it's
the opposite, right? You get an XRD back, and you see that there's a particular Q vector that gave you an answer, that gave you signal. Then you can ask, what kind of crystal do I have? Because from that Q vector, now you extrapolate to the position of what planes are contributing to the XRD.
Yeah. Inversely, that would tell you what your Miller indices should be. And from there, you can probably go back to the basic lattice structure as well.
Exactly. Yeah.
Okay, that's the basis of that separation between planes. Okay, that makes sense. Thank you.
All right. So if there's no other questions, that's where we stop. Next class is going to be also online because it's too cold. And it's going to be at the normal time, 4:30 to 5:45. Okay. The colloquium got moved to, I think, 1 o'clock, I believe.
Yeah, I think they changed it to 1, for at least for this week. Yeah.
Yeah, exactly. So we don't have to move our class.
And you're going to upload this in YouTube, right? This video.
This is going to be uploaded.
Because this lecture was kind of a little complicated. I'll have to look at the whole